Okay, so our next topic is inverse of a matrix. So suppose if A is any square matrix and B is a matrix such that A into B is identity matrix. B is also a square matrix. So I have a matrix A and another matrix B, and the product of these two matrices is identity matrix. So in that case, if this condition is satisfied, then we say that B is inverse of A, or you can also say that A is inverse of B. So if product of two matrices is identity matrix, then second matrix is called inverse of first matrix. Now we have seen that if I have a matrix A, then A into adjoint of A, this was determinant of A into identity matrix. This was the relation that we have discussed earlier. So A into adjoint of A, this will be determinant of A into identity. So I can rewrite this relation as A into adjoint of A by determinant of A, this equals to identity. Now you can see that you have one matrix A, another matrix adjoint of A by determinant of A, and the product of these two matrices is identity matrix. So this means the second matrix is nothing but inverse of first matrix. So I can write that A inverse, this will be nothing but adjoint of A, this divided by determinant of A. So this is the formula to find inverse of any matrix, adjoint of A by determinant of A. We have learned how to calculate adjoint. Adjoint of matrix is you have to form a matrix by cofactor of each of the elements, and then you have to take transpose of that matrix. Now inverse will be nothing but adjoint of A, this divided by determinant of A. Now see, in order to calculate inverse of matrix, you have to calculate two quantity. First you have to find adjoint. One you have to calculate adjoint, and second you have to calculate the determinant. Now always calculate this determinant first. The reason is that if determinant of this matrix, if you calculate the determinant of this matrix, then there are two possibilities. Either the determinant is non-zero or the determinant is 0. Now the moment determinant is 0, in that case the inverse will not exist. This denominator cannot be 0. So if the determinant is 0, this implies A inverse does not exist. And in this case, if determinant is 0, then the matrix is called singular matrix. So for a singular matrix, the definition will be determinant of that matrix is 0. So for singular matrix, inverse will not exist. And if the determinant is non-zero, only then A inverse will exist. And if determinant is non-zero, then in that case the matrix is called non-singular matrix. So for non-singular matrix, the condition will be determinant of that matrix is non-zero. So in order to calculate inverse, you have to find both adjoint and determinant. Now first calculate the determinant. Only if the determinant is non-zero, then A inverse will exist. And if the determinant is non-zero, then A inverse will not exist. And these type of matrices are also given this singular and non-singular name. So singular matrix means determinant is 0, non-singular means determinant is non-zero. So inverse is possible only for non-singular matrix. Now after this, we have to learn some important properties of adjoint and inverse. So next heading will be properties of adjoint and inverse of a matrix. Properties of adjoint and inverse. So total we are going to see 7 properties. So our first property will be, this we have already discussed earlier, but this is very important property. So I'm again writing this. A into adjoint of A. This will be adjoint of A into A, and this is nothing but matrix A into identity matrix. So this was first property which we have discussed earlier. Now the second property is, and this is very, very important, reversal law for inverse. Reversal law for inverse. We have seen the reversal law for transpose of matrix, and there we had said that if this reversal law will come at 3 places, one at transpose, another for inverse, and the third one for adjoint. So the reversal law of inverse is that if I have two matrix A and B, then inverse of AB, this will be nothing but B inverse into A inverse. And if you want to prove this relation, then it is very easy to prove this relation. See, you have one matrix AB and another matrix B inverse A inverse. Suppose if I multiply these two matrices, then what I will get? I will get, we can write B and B inverse as identity matrix. B into B inverse, this will be identity. So you will get A identity A inverse, A into identity, this will be matrix A. So A inverse, this will be identity matrix. So you can see that you have one matrix AB and another matrix B inverse A inverse, and the product of these two matrices is identity matrix. So this means the second matrix is nothing but inverse of first. So second matrix is inverse of first matrix B inverse. Second matrix B inverse A inverse is inverse of first matrix AB. So this law is called reversal law for inverse, and this law you can extend for any number of matrices. If I have three matrices, say if I have three matrices A, B, C, and we want to calculate the inverse of this matrix ABC. So the inverse of this matrix ABC, this will be C inverse into B inverse into A inverse. So this is our second property, the reversal law for inverse. The third one is reversal law for adjoint. Reversal law for adjoint of a matrix. Now see, we have defined the inverse of a matrix as A inverse. This was adjoint of A, this divided by determinant of A. So this means you can write adjoint of A as determinant of A into A inverse. So you can see that adjoint is nothing but inverse multiplied by some number. This determinant of A will be some scalar quantity, some number. So adjoint is nothing but inverse multiplied by some number. So if a property is true for inverse of the matrix, then it has to be true for the adjoint also. So the reversal law of this adjoint of a matrix is adjoint of A into B. This will be adjoint of B into adjoint of A. So this law is called reversal law. Adjoint of AB is adjoint of B into adjoint of A. And again you can extend this for any number of matrices. So this is our third property, reversal law for adjoint. Now our fourth property is, this is very basic property. If you have to calculate the inverse of, if you have to find the transpose of inverse of a matrix, then you can write this as A transpose inverse. You can interchange inverse and transpose. So this will be our fourth property. Next, the fifth one is determinant of matrix A inverse. This is nothing but 1 by determinant of A. Now again, this is obvious property. If you have to find the determinant of inverse of a matrix, then you can write that as 1 by determinant of A. So these are first 5 property. Now after this, the other 2 properties are very important. So next we are going to see property number 6, and this will be to calculate determinant of adjoint of A. So our sixth property is determinant of adjoint of A. Now this determinant of adjoint of A, this is nothing but determinant of A to the power n minus 1, where n is the order of matrix. N is order of matrix. So this is very important property. Suppose if I have a matrix A whose order is say 4 into 4. So in that case you can write that determinant of adjoint of A, this will be determinant of A to the power 4 minus 1. So this means determinant of A cube. Now we are going to prove this result, that why this result is true. So the proof of this result is, we know from the first property that A into adjoint of A, this is nothing but determinant of A into identity matrix. This we have seen earlier. Now we are going to take determinant on both sides. So I will get determinant of A into adjoint of A. This will be determinant of A into identity. Now we also know that if I have two matrices A and B, you can think of this matrix as A and another matrix B. So you can separate the determinant. So we can write this as determinant of A into determinant of adjoint of A, and this will be, now see here we have to apply one very interesting property. This we have discussed in multiplication of a matrix by a scalar. If K is some number and A is a matrix, then in that case determinant of K into A, this will be K to the power n into determinant of A, where n is the order of matrix, because we had to multiply each element of this matrix A by this number K. And in case of determinant, you can take K common either from a row or column. So here also we have to use the same property. This determinant of A is some scalar quantity, this is K, and here I is the identity matrix. So if I want to take this determinant of A outside, we have to take nth power of this number outside. So this multiplied by determinant of identity matrix. So now I will get determinant of A into determinant of adjoint of A, and this will be determinant of A to the power n, and determinant of identity matrix we all know is 1. So if I rearrange this relation, then finally you will get determinant of adjoint of A. This will be determinant of A to the power n divided by determinant of A. So this will be determinant of A to the power n minus 1. So this is very, very important property. So after this we have to learn the last property of this inverse of a matrix, inverse and adjoint. So our seventh property is, property number 7 is adjoint of A. This is determinant of A to the power n minus 2 into matrix A. So this is our seventh property. Here again n is order of the matrix. So, and again we can prove this result using this identity itself. If I want to prove this result, then we have to start from here. A into adjoint of A. This will be determinant of A into identity. Now see, this relation is true for any matrix. A into adjoint of that matrix A, this will be determinant of the matrix A multiplied by the identity matrix. So you can replace this matrix A by any other matrix. So in place of A, now I am going to write adjoint of A. Adjoint of A is also a matrix, so I am going to replace this matrix A by adjoint of A. So I will get adjoint of A, this multiplied by adjoint of A, and this will be determinant of adjoint of A into identity matrix. I have simply replaced A by adjoint of A, so wherever I have this A, I am writing adjoint of A. Now in the next step we are going to multiply both sides, multiply by matrix A, and we are going to do pre-multiplication. So this means both sides we are going to multiply this, multiply by matrix A first. So I will get A into adjoint of A, and this multiplied by adjoint of A, and this will be, here also we have to multiply by matrix A. So I will get A into determinant of adjoint of A. We already know this is nothing but determinant of A to the power n minus 1. So here I will get determinant of A to the power n minus 1 into this identity matrix. Now A into adjoint of A, from the first property we know that this is determinant of A into identity. So I will get determinant of A into identity, this multiplied by adjoint of A, and this will be determinant of A to the power n minus 1. A into identity is matrix A. Now you can see that if I rearrange this relation, if I divide both sides by determinant of A, identity into this matrix is this matrix itself. So finally you will get adjoint of A, and this will be, if I divide this by determinant of A, I will get determinant of A to the power n minus 2 into matrix A. So again this is a very, very important property. So these are 7 properties of inverse and adjoint of matrix. After this we'll take some of the problems on inverse of matrix.